Thank you so much, Ikai, for inviting me. It's great to be here again. So many of you I know, so it's really wonderful to be back. And please come on in. There's plenty of seats on front. There are other people as well, so if they want to, they're welcome to. So can you see the screen, or should we pull down some shades? It's your call, right? It's really up to you, but that's also good. All right, well, it's gonna be a dark day. Okay. So actually, somebody mentioned yesterday, I could have probably talked about this new quantum supremacy stuff, but I totally forgot about it. It's one of those results I just put out and forgot about. So, um, so I'm going to talk about this. So maybe it would have been better for the audience. I don't know, but it's also not a bad result. It is pretty dark now. So the terminology, supercritical entanglement, counterexample to area law for quantum matter. I'll define all these things, like what I mean by supercritical, etc. So my goal is to present to you, do a little bit of background about area laws for entanglement entropy, and tell you what was expected, and then show you a class of models that do surprising things. Like they have a lot of entanglement. That's my goal. And since the audience is, they've heard of basic notions of quantum stuff, so I can skip some of the really basic stuff. So Feynman in his crazy way proposed a quantum computer in 1981, published it in 82, that like there's this exponential number of resources you need to do a simulation of quantum matter, but if you have a quantum computer, you can do it efficiently because it's quantum, it can simulate something like itself. And that would be great because if we did have a quantum computer, among other things, we can do a more serious study of matter, like we can simulate larger systems, understand maybe better understanding of high temperature superconductivity, simulate small molecules and proteins, maybe not proteins, but molecules and cells, quantum chemistry, have a better understanding of quantum phase transitions, etc. One thing that seems to have a lot to do with how well we can classically simulate quantum matter versus not is the so-called entanglement. So this is not 100% true. I mean, there are systems that are very entangled, but easy to classically simulate. But this is something that needs to be understood better. But in many cases, it is true that if a system is low entangled, then it can classically simulate. So let me just quickly say what I mean. Suppose you have a joint system, composite, A and B. So in your mind, you think of it as two pieces, A and B. So there is a joint ground state, psi AB. If you cannot write it as a tensor product of psi A and psi B, we say it's entangled. That's the definition. So it's not in a product state. And then the question is, well, how entangled? One good measure is the von Neumann entanglement entropy. So you trace over A or B, it doesn't matter. So you get a reduced density matrix, rho A, and minus trace rho log rho is a measure of entanglement, it's the entanglement entropy. All right? And it's very different from thermal entropy. So if you have a joint system that's in a pure state, it has zero entanglement, right? I mean, it's one pure state. But you cut it in half, and the entanglement entropy goes up. So this is an indirect way to say how much quantum correlations there were before you threw half of the system out. Okay, so entanglement and thermal entropy are very different in that sense. Like thermal entropy, if you double the system size, by extensivity, you expect that the entropy goes up twofold. Here, you double the system size, entropy goes to zero. You cut it in half, you generate disorder. Okay, so it's an indirect way to say how much quantum correlations there were before you chopped half of it between A and B. Fine. So one can ask some meaningful questions. Like, for example, if you have a system in D spatial dimensions, and the linear size is L, suppose there are L spins in so each side has L spins. Then you can ask, what generically, how entangled is A with B, right? And it turns out that generically is actually volume law extensive. So you can prove that the entropy between A and the rest of the system generically goes as L to the D, where D is the spatial dimension, L is the linear size. And this was proved, that with probability 1, this is the case. So you grab a random Haar state in the joint Hilbert space, you trace over half of the space, and you get extensive amount of entropy. Okay? But a Haar state is not a type of state that you expect in quantum many-body systems. There's no reason why the ground state of a quantum many-body system should be a Haar state, like a totally random state. For example, the constraint of locality, so for most models we know, interactions are local, so it's an algebraic way of writing this. So they say nearest neighbor interaction or k-local. Moreover, we don't care about just some random state. We usually care about the ground state. And the gap is also important to the first excited state, because if the gap goes to 0, then it could mean that with very small fluctuation, you could go from one macro state to another macro state in the thermodynamical limit, and that's a quantum phase transition. So understanding the gap is also important. Another thing we have learned from experiment and from physicists is that there's a notion of translational invariance. That is, if you have a clean system, the interaction in nature is a function of distance. So if there are two electrons sitting next to each other somewhere on the lattice, there's no reason why they should interact differently if they were somewhere else in the lattice. So translational invariance for a clean system is a very natural assumption. So under these set of assumptions, the ground states will probably not be just some Haar random states. They may be something else. And we've actually learned over the years from physicists that you expect the so-called area law. What's an area law? It says that if you trace, so if this is your A, everything else is B, and the system, so maybe I say one other thing. We say a system is gapped if this delta is lower bounded by a constant as you take the system size to infinity. Right? As in the thermodynamical limit, this delta is always bigger than a constant, so it's a constant. We say the system is gapped. There's a constant gap. So the belief is that if you have a gap, then the entanglement entropy doesn't go as L to the D, but goes with the boundary, L to the D minus 1. Right? And it's called an area law because the name came from black hole physics, and the surface is an area. It should really be called a boundary law. Like in one dimension, the area is just a cut, so it's a number. It's just a constant. 3 dimensions, the area is a surface. But in higher dimensions, it's just L to the D minus 1. And then the belief was that, if you have a critical system, so the gap goes to 0, and, correlation functions diverge, then you don't go all the way to L to the D, but you get just a logarithmic correction. So it's still, so log of L is exponentially smaller than L. If there were an L here, you would get L to the D. But, so you just get some logarithmic prefactor. That was the belief. And this belief is enforced. This belief comes from basically some really robust set of arguments in 1 plus 1D systems, critical systems describable by conformal field theories. And log L is what you expect there. So this is a work that started with Wilczek, then Cardi, Calabresi, and then Korapin and many other people. But I'd like to emphasize that the only place we have a real proof, mathematical proof, is if a system is gapped and it's in one dimension. If you have a gapped 1D system, you can prove the area law. So Hastings did it. So the entanglement entropy is L to the 1 minus 1, 0, so it's a constant. Okay? But there's no proof elsewhere. It's a belief based on, experience or, like good arguments, etc. Right. And, like some of this search for exactly solvable models that have surprising features, entanglement, etc., started with some original papers, like Haldane, for example, said that, like there's a difference between integer and half-integer spins. And then AKLT came along, inspired by that paper, and gave an exactly solvable set of models where entanglement entropy is actually a constant, system is gapped, they could prove it. This gave rise to this idea that 1D systems are easy. Eventually, we had DMRG, matrix product states, etc. And this idea of area law really works in 1D. Like people, calculate 1D systems and publish in Nature and Science, so it must work. Right? So they use DMRG. They calculate all sorts of things. Huh? It doesn't work? Oh, I see. Okay. Yeah, so the reason, so this DMRG and matrix products, they make use of the fact that they can chop the Hilbert space down to small sizes because the entanglement is low, by ignoring some Schmidt numbers. And therefore, you can make these calculations, and they agree with experiment. And when they agree with experiment, well, then you can publish in Nature and Science, right? That's right, that's right, success in publication. And this is great. So we actually, like in 2012, we came up with a set of exactly solvable models that saturate that log L that you expect from critical systems. The title of the paper does have criticality in it, but by now I'm pretty sure these models are not critical in the strict sense of the word. They're gapless, etc. There's a log L amount of entanglement, half-chain entanglement. You know, it's a spin one chain, etc. And the belief, again, the belief was that you can never do more than log L in one-dimensional systems if they're physical. So what do we mean by physical? By physical, you mean not fine-tuned. So there's a paper by Brownian, for example, where they actually lay down a set of conditions that I really like, and it kind of makes it helps us understand like what we're supposed to call physical versus not. So you know, if you relax any of these, you can do very funky things with the ground state. So you want to have a unique ground state. You don't want like some highly degenerate ground state, because then you can do all sorts of crazy things. You want to have a local Hamiltonian. If you have like a global Hamiltonian, if you came to my talk yesterday, if you have like one big random matrix on your spin chain, well, the states of this random matrix are going to be Har. And by the theorem I just showed you a few slides ago, it's going to be maximum entanglement entropy, because it's generic. Right? So locality is another thing. And imposing translational invariance is also physical. Right? I mean, all of these, like if you have disorder, you don't have strict translational invariance. But if you're going to come up with a result, exactly solvable model, that convinces your physicist colleagues, they would take you serious if you satisfy these, okay? Like there are these rainbow states that have high entanglement, but they're fine-tuned in some ways. Okay, so under these set of assumptions, the belief was that you can never do more than log n. So I'm switching between L and n because I'm gonna go to spin chains now. So n is the number of spins, and that's the length of the system. So we came up with a set of with a class of models where the entanglement entropy is actually square root of n. So it's exponentially more than log n, okay? And they satisfy these assumptions, basically. So my goal is to tell you about these models and tell you about follow-up work. And if there's time, I tell you about the proofs of the gap, etc. So that's my favorite part. There's a lot of fun math, but I don't know if we'll have the time. We'll try, okay? So this is the background I wanted to give. Any questions before we get into the models? Or maybe comments, or whatever? It's clear so far what we're trying to do? So now I'm going to give you an example, like a particular model. Yes? Right. So that's a good question. So you need to be gapless to be critical. But, so excuse me. Yeah, gapless is necessary for criticality. But it's not sufficient. In that, so if you want to have criticality, you need a critical point, right? If you tune to it. So if your Hamiltonian is a function of a parameter, you can tune to a point and get a second order discontinuity in the ground state energy as a function of that tuning parameter. And to its left, there should be one phase. To its right should be another phase. And at that point, there should be divergent correlations, right? So these are much stronger than just gaplessness. So it does happen, actually, often in literature. You see that you have translational invariance and you have gaplessness. You just call it critical. That happens a lot. But that's not strictly correct. So these are translationally invariant, and they are gapless. But, you know, we're not just going to say they're critical. Any other questions? So the implications are, I mean, one is like epistemology of area loss. Like can quantum matter be, how entangled can it get? One. Second is, are there set of examples that are physical that DMRG or matrix product states would choke on? That is, they wouldn't be able to approximate well because they're not classically simulable. Third is like, if you have a lot of entanglement, usually believe you can utilize it for quantum information processing. So just right. I mean, there are many answers that could be given, and class of exactly solvable models is always good to have because they give rise to new understanding and maybe other models that can be built. And we have to develop some new mathematics. So that's also always of independent interest. Yep. Yep. Yeah, that's what I'm defining to be that's what I'm defining to be unified. Or physical. Physical. Fine-tuned is a little stronger. You need some robustness maybe with respect to perturbations. And these models do have some robustness with respect to perturbations. But maybe I should have said physical. Okay, so I want to tell you about these models now. All right, so the outline is going to be that I first give you the ground state. We call it the Motzkin state. And the techniques, mathematical techniques, are going to be some combinatorics of random walks, some information theory. So I first give you the ground state, then I prove area law stuff with the promise that there will be a Hamiltonian, okay, whose unique ground state is the Motzkin state. So it's backwards. Usually in physics, people give you the interaction, then you go study its properties. So here, I'm first giving you a ground state with the promise that there will be a Hamiltonian that is local, translationally invariant, etc. That will have the state that is unique ground state. And then I'll tell you some follow-up work on our work, so like some other new models, etc. And if there's time, I'll prove that the gap goes as 1 over a polynomial in n in the system size. So it closes slowly. It's not exponentially small, and it's not obviously it's not gapped because there's a lot of entanglement. Okay? Does that sound good? Okay, so suppose we have a spin 1 chain for simplicity. So if S is 1, there are 3 states, plus 0, minus, right? But there are D2S plus 1 states. I'm going to label them not as plus 0, minus for reasons that will become clear soon, but as a step up, 45 degrees, a flat step, and a step down. Okay, maybe plus 1, 0, minus 1. And if the spin is greater than 1, oh, by the way, these are going to be integer spin models. Okay, so that's spin 2 now. Then I have 5 states, and I can have a step up that is red, and a step up that is blue. Orthonormal. They're orthonormal bases for the local Hilbert space. Now I want to emphasize these do not anymore correspond to plus 2, plus 1, 0, etc. Just think of them as a new labeling of the 5-dimensional Hilbert space locally on this spin. Right? They don't correspond to like your standard spin eigenvalues. And the flat step is never colored. Okay? So every spin has this label on its spin values. Now, let me introduce a Motzkin walk to you. A Motzkin walk, so is any walk. So if so the size of the chain is going to be 2n. So n was taken to be 5. So I can meaningfully talk about a half chain. I mean, if it's odd size, it doesn't really matter. It's just that I don't want to worry about what it means to have a half chain. So the chain is 10, n is 5. A Motzkin walk is any walk that starts at height 0, ends at height 0, never goes negative. I mean, it can hit 0, but it never goes negative, and is made up of exactly those 3 steps, up, down, and flat. Okay? So this is an example of a Motzkin walk. And my ground state is going to be a uniform, so maybe belabor the obvious. So what this means is that the first spin here, this is a product state now. The first spin is in this state, up. Second spin is in down state. Third up, etc. So together, it makes a walk. And this is a Motzkin walk, some type of walk. there are other walks that could go, down, 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 for example. But those are not going to be our ground state. We're not interested in them. And the ground state is going to be a uniform superposition of all Motzkin walks. This is just with the promise that there will be a Hamiltonian. So suppose we have a uniform superposition of Motzkin walks as our ground state. Just to give you a little bit of intuition, the reason there is so much entanglement between the left and right is that from Brownian motion, you might remember that the height in the middle goes with square root of n, right? And so there's some steps here that do not get balanced till all the way to the right. So there's some so even classically, there's some mutual information between the two halves. So the right knows something about the left. And if there are colors, it's the same story. You have a Motzkin walk again, except that a blue balances blue, and a red balances red. So you cannot do, so you can do blue, red, red, blue, but you cannot do blue, red, blue, red. Even if the numbers match, the ordering matters. Right? So if you think in terms of like, if you think in terms of parentheses and braces, so if this is a left parenthesis, right parenthesis, left braces, right braces, so these are the set of bracketing that do not give you like errors on LaTeX. So you can't do parentheses, braces, parentheses, braces. You gotta do braces, parentheses, braces. Okay? So ordering matters. So for example, if s equals 1 and I have only 2 spins, my whole chain has only 2 spins, n equals 1, this is the ground state. Flat, flat, plus up, down, with some normalization. And if n is 2, well, chain is 4, then, well, these are all Motzkin walks. You can convince yourself. There's 9 of them. If spin is bigger than 1, say 2, well, I can have an up, down of any color, blue or red. Okay? And similarly here, I could come and color them, but the slide would get pretty long. But you get the idea, right? So this is the ground state. So what I have to do now is consider a long Motzkin walk, chop it in half, that is, take a partial trace, and calculate the entanglement entropy. Yeah. For now, yes. Well, ultimately, no, but this is an open boundary condition so far. To meaningfully talk about a beginning and an end, right, and height in the middle. The result does hold, but it's less worked out. So so you have to make a tweak to the model, like add a small external field and get everything, like you get something close to the Motzkin chain. But it's not as, it's in the paper, but it's not as explored. But you will see boundary conditions play an important role in here. Okay. So, so after taking a partial trace, you work for a month and a half, and you get this formula. Okay? So there's an exact formula, then you do asymptotic analysis on it, you do your things correctly, hopefully. It involves some random walks, etc. I could show you the calculations, but okay, it's a calculation. So this capital is an entanglement entropy. Yeah, I'm not going to show you now, but so it will be, this approximation is because some of the summations were taken into integrals in a controlled way. It's not a big approximation. Asymptotically, it's correct. So you get to the leading order square root of n. Sigma is just a constant that depends on the spin. So if s equals 1, so little s equals 1, log of 1 is 0, right? So you have half log n plus some constant. Gamma is Euler constant. And these are just constants. But as soon as s is bigger than 1, so you have s equals 2, which has 2 colors, or s equals 3, which has 3 colors, so blue, red, and green. So these violate the area law by square root of n. Okay? Now, you might say, well, maybe you did your asymptotic analysis wrong. Maybe you think you get square root of n. So the red dots here are exact, based on exact summations. And the black curve you see is the formula I just showed you, which is supposed to be approximately true and only exact in the limit. So when s equals 1, you get logarithmic, and you see that it's working very well even for small n. And for s equals 2, 3, 4, etc., it does have that power law, and it's becoming exact asymptotically. Okay, so the red dots are exact summation for small sizes. Before, it has factorial things in it, combinatorics, so n choose k's in it, and at some point, MATLAB can't handle it anymore. But so, okay, so I gave you the state, Motzkin state. Do you have any questions on the state? I want to tell you the Hamiltonian now. So, right, we have the promise was that it's a unique ground state. It's a superposition of many things, but it's one state called the Motzkin state. It violated the area law by square root of n. The Schmidt rank is exponentially large. I didn't show it, but it is. And I'm done. So I want to tell you about the Hamiltonian. Yeah. Yeah. Yeah, it's a good question. It doesn't decay too fast. At some point, I knew the exact answer to it. I don't remember right now, but we can talk, and I can show you. But the number of them is going to be exponentially large, and part of the reason we got into these models was originally we wanted to show limitations of DMRG for like random local interactions, but we just couldn't do that. And at some point, it became clear that if you want to prove that, you just need one example, because there's an argument from algebraic geometry. You can show that if there's one example, there's an open neighborhood around it, so it'll be with probability 1. But we kept building examples, but they went the other way, like the rank was too high or whatever. But these examples became more and more interesting, and at some point we had the Motzkin stuff, and they took a life of their own. So I don't even talk about where these models came from originally. But yeah, so the goal was always to find some limitations for DMRG. I mean, this does show a limitation for DMRG. It still has too high a rank. Yeah. Yeah. Right. Yes. Oh, you want to know the intuition? Yeah. So root n in the middle. So the amount of information between left and right is log of the height of the root n. That's half log n, right? Because it's n to a half. Now, if you have colors, you take root n steps on the left that have not been matched, right? I mean, they're correlated with the ones to the right. For any coloring of the left-hand side, you get a unique coloring on the right-hand side, right? So how many ways are there to color the root n steps? S to the root n. You take a log, you get root n log s. Okay? But they're constants, and to do exact answer. But intuitively, that's the reason you get root n. Why? No, not that I know. But maybe somebody can. They're stochastic, so maybe you can do quantum Monte Carlo. You will see that the Hamiltonian is stochastic. Maybe you can do quantum Monte Carlo. I don't think anybody has done it. Okay? Other questions? Hamiltonian. So the Hamiltonian will be local. So that's a local Hamiltonian. It's going to be nearest neighbors. And every one of the local terms is going to be a projector. So the ground state actually is going to be a frustration-free ground state. But that's a minor detail. So the local projectors will implement the following moves. So from now on, maybe it's good to think of a step up as a particle, step down as an antiparticle, and flat as vacuum. All right. So if you have an antiparticle, it can go through vacuum. I just exchanged them. Or if you have a particle, it can go through vacuum. So it's symmetric with respect to exchanging position. And if a particle and antiparticle reach each other, they annihilate to vacuum, vacuum. Or vice versa. You can go from vacuum, vacuum to spontaneously create a pair. All right? And like similarly with the reds. So I didn't put, so if S equals 2, there's such moves with red colors everywhere. And when we say symmetrically, what it means is that you have a projector that projects onto this state. So you look at this cat, you multiply it by the same broad, that's a projector. So it gives an eigenvalue 1 to the antisymmetric state. Therefore, it treats the symmetric part symmetrically. so the symmetric part is in the kernel of the local terms. And one of the things was that I told you that the ordering mattered, right? You cannot do blue, red, or red, blue. And you give an energy 1 if you have a red, blue, or a blue, red, right? So this is a projector, also local. It gives you energy, it gives you eigenvalue 1, which is penalizing wrong ordering. Okay? So for example, if S equals 1, that is your Hamiltonian. So HJJ plus 1 is this projector plus this projector plus this projector, and this ket is defined to be simply this, this, and this. So just no colors, right? And I don't have to worry about the other term for penalizing wrong coloring because there's only one color. Now with these moves alone, there is no way that you can start from height 0 and end at height 0. I mean, the condition of 0 height doesn't come into any of these terms. The way you enforce that, maybe just a little bit more. So under these moves alone, if you start from any given height and you go to any other given height, the initial and final heights are constants of motion, or they're conserved. Because like all the local moves are height preserving. So uniform superposition of all walks with this initial and final height will be a ground state. So it'll be a degenerate ground state. So the ground space will have a dimension greater than 1. Motzkin state is the only state that starts at 0, ends at 0. That means the initial step can never be negative, so it can be flat or up, and it can never end like this with a step, it can never end like this with an up. It should be flat or down, and it can never start like this. And in order to enforce that, you just add these boundary projectors. So on the very first spin, these dots mean colors, all right? So if there's more colors, there are more terms. If there are 2 colors, that's all there is. So in the first one, you project out any walk that starts negative of whatever color. And you similarly project out or penalize any walk that ends like this, that is, has an imbalanced last step. And this will uniquely select the Motzkin state, uniform superposition of all Motzkin walks, as its unique ground state. Okay. So now we have a local Hamiltonian whose unique ground state is the Motzkin state that violates the area law by square root of n. So that was the Hamiltonian. Any questions on the Hamiltonian? So these are projectors, and they're frustration free by construction. And the frustration freeness will imply that any 2 walks that are related by local move have the same amplitude. And if they have the same amplitude, you can go from any walk to any other walk. Therefore, they must all have the same amplitude. And it's going to be uniform. Any other questions? Okay. So let me just summarize. Okay, so I want to tell you about some of the follow-up work on this work, not my work, but other people who've gotten into it, and summarize what we have, and we'll have some time, and I'll tell you about the gap. So I just showed you an integer spin chain model that has to the leading order square root of n violation of area law for s bigger than 1. And the Motzkin state is the colored Motzkin walk. These are some references. And the gap, actually, the gap scales as 1 over n to a constant, where we can prove that constant is bigger than 2 and smaller than, I think, 9 halves. Okay, so it's really a polynomial. And since then, there have been some generalizations. There's this Fredkin spin chain by Korpin and Solberger, where they just do what we do, but for half integers. And they get similar scaling, everything the same. So if spin is, if you have a spin half particle, they get logarithmic. And if spin is 3 halves or more, you get root n. And they have the colored Dick walks, which I'll explain. And another thing, which goes back to your question about like root n. So the middle height is root n, right? Like from universality of Brownian motion. But what if you come and prefer taller walks in your ground state? Well, then you can take that expectation to n if you find a way to do it. And there's a way to do it. And then, you get n. That's exactly what these guys did. So they weighted it. I will explain these. So both these nice results, they couldn't prove the gap for their models, unlike us. So they just have the state and the Hamiltonian. They couldn't prove the gap, but that's okay because now we have the gaps. The gap of this model is actually just like ours. It goes as 1/n to a constant. But entirely a different proof technique was needed here. It's just a different model. And here, the gap is exponentially small in the system size squared. It's just like really small. I mean, I'd never seen something this small. I mean, exponentially small for gap systems, but exponentially small in the system size squared. Naive gap will give you exponentially small, but if you do it carefully, you get exponentially small in the system size squared. And so we know the gaps of these models too. So I want to briefly describe these models to you, just like what they achieve. So first we do in the opposite. I give you number 3 first. So actually, this is inspired by our proof for the gap, which I'll get to. So suppose instead of all the Motzkin walks, uniform superposition of colored Motzkin walks, every walk gets pre-multiplied by some real parameter t. So t is greater than 0, but some real number, to the power of area under the walk. This is kind of what we use for the gap. But you can also define ground states like this, so t to the area. Now you can see that if the area is large, the term gets a much bigger weight. Actually, exponentially large. If t is bigger than 1 and the area is large. And that takes the height in the middle to n. It just does, right? I mean, it just prefers really tall walks. And that gives you maximum possible, which is n. And I already told you that the gap is, exponentially small in the system size squared. And interestingly enough, every time you want to prove one of these gaps, you can map the result to a classical Markov. Well, not every time, but like you can map the result. You can map the quantum model to a classical Markov chain. Then every time it's been fun. Like it's a new Markov chain. You got to prove its gap. It's just some really interesting combinatorial thing that you have to prove the gap for. Here, all we needed was an upper bound, so we didn't have. Yeah, it was less of a hassle than both ways, upper and lower bound. And the Fredkin spin chain is just like our model, but without flat steps. So the fact that you don't have a flat step gives you half integer models, right? D equals 2, S is half, 4, 3 halves. And the ground state will be a uniform superposition of all Dick walks, they're called. So these are Catalan walks. They are counted by the Catalan numbers. So it's a uniform superposition of all such walks. Start at 0, end at 0, never go below 0, and right ordering, just no flat steps. That's it. And the Hamiltonian here, there is a theorem that says if you have a frustration-free spin half chain, the ground state must be trivial in terms of entanglement. So if the interaction is strictly local. So their interaction is actually 3 local. So 3 consecutive spins, any peak can exchange position with a given step. So you see, if you move this peak to the left of the step up, you get this. And vice versa. If you grab this peak, you move it to the right, you get that. So this is what they treat as symmetric. Similarly here, if you have a peak, you move it to the right of a step down, you get this. And from here, if you move it to the left, you get this. Now, so maybe can you entertain the following thought? In your imagination, just imagine flipping this peak down. So, from here, you go to here. You get that. And vice versa. If you flip this up, you get this. And similarly here, if you flip this down, you get this, and vice versa. You get that. So this is what I tried to use, and I can tell you, I worked really hard to make this work for proving the Markov chain, to get the gap of this model. And there's one big problem, and that is, so if you just have this flip, this to this is called an ASEP, asymptotic exclusion principle. sorry, asymmetric exclusion principle. Actually, this is CSEP because it's even symmetric. But the thing is, so lot is known. So there we know like the mixing time is t cubed log t, n cubed log n, etc. But the problem is that this maps almost to this. Like if you have 2 step downs and followed by 2 step ups, the A step will flip the valley, but this will not. And that difference really kills it. I mean, the techniques just did not transfer because of this simple thing. I mean, if you have valleys that are deeper than, 2 height, the techniques would not transfer. So I needed a whole new, after like months of it not working, but we got we have the gap now. So the gap actually goes as 1 over n to a constant, like I told you. So, for spin half, you get log n. For spin bigger than half, you get square root of n. And so that's another follow-up model on this Motzkin spin chain business. Yeah. Yeah. Yeah, yeah. So that's a very good question, and there's a conjecture on it. So it's price on its head, and it's been open for a while. Nobody has been able to prove. So there is a conjecture that relates the gap scaling to entanglement entropy scaling. And one would hope, like you said, one would hope that one can prove something. I don't have such a proof, and I think many other people have tried. And so the short answer is that it probably is possible, but we just don't know how to do it. All right. Okay, other questions? So some references if you want. So I didn't tell you about correlation functions, the symmetry. Like suppose you don't do a half chain entanglement entropy, but you do like a cut about somewhere else, or you grab just L consecutive spins in the middle and you look at their entanglement with the rest of the chain. And maybe you want to know how the Hamiltonian looks like in standard spin representation, like if you want to implement it in an experiment or whatever. So those are in this paper. So these have been worked out here. And the rest of it I told you about. Okay? So if there are no questions, I want to tell you, yeah. Yeah. Oh yeah, I didn't, but there is one. So yeah, so good. It's just like ours, but like the height. Yeah, I should have. I didn't. So there's this move that goes to this move, right? So this gives you a bigger area. This has area half. This has area 1 plus a half because of the square that is made here. You multiply this by. They're local, just like ours, but you multiply the one that gives you bigger area by t. There was t to the area under the walk, remember? They're all local projectors, and the area comes out of the fact that locally you multiply the projector that gives you a higher weight, you prefer it by t. And it turns out, so it's actually, like technically it was nice what they did. I mean, it seems trivial, like from intuitive perspective, but the fact that they multiplied it by t, and they got that t to the area as the unique ground state, and they could prove that's the unique ground state, that's frustration free. I mean, technically it was work. Yeah. It wasn't just, I mean, intuitively, if you look at the proof of our gap, you would expect it could do that, but to actually make it work was impressive, I thought. Yeah. You would think, I don't have any, but that's a good future work. I mean, one way of talking about higher dimensions is introducing colors, but still a spin chain. But if you mean spatial higher dimensions, you probably would be looking at random surfaces. I don't have such a construction. I haven't seriously worked on it. I was hoping somebody else would do it, so maybe you can do it. Yeah. Yeah. So that's actually, if you look at this, I mean, I don't know about like one particular spin, but suppose you take L spins in the middle. Okay, there's a formula here. Also goes as log L, and then with the student, we're generalizing it to colored case, so that's also square root of n. I didn't show it, but yes. Other questions? Okay, so, okay, I want to tell you about the gap, because it's like, this was the hardest part. Like, proving the gap is usually hard, but it's also fun, and I think some of the techniques may be useful to general, for you in other contexts. So the gap is, to calculate the gap exactly is something we couldn't do. It was too hard, like to give you exact scaling. We believe like C should be 3.17 based on DMRG. But, I mean, we couldn't prove it. But what we can prove is that it's polynomially small. And the way you prove that is that you show that the gap is always smaller. So the energy of the first excited state is always smaller than 1 over n2, 2. And is always larger, so it's lower bounded by 1 over n2, a bigger constant, which in this case will be 9 halves, I think, or 11 halves. So therefore, the gap is a polynomial. I mean, it closes polynomially with n. Okay, so I'm going to show you the upper bound and lower bound. So to get an upper bound, so upper bound meaning, by upper bound I mean just this. So generally, to get an upper bound, this slide has nothing to do with this particular model. This is how you prove upper bounds. You grab any state phi, and suppose you want to prove a gap that's 1 over n squared. This is what we believe we could prove. So any state phi can be expanded in the orthonormal basis of the Hamiltonian, because it does provide its eigenvectors span. So alpha 0 is some unknown coefficient times the Motzkin state, which is the zero energy state, plus alpha 1 times the first excited states, etc. Now you demand that the state that you chose has some constant small overlap with the actual ground state. Say half. Doesn't have to, could be a third. And if you look at phi h phi, if I put this in here, you just get this, because these are eigenstates and they're orthonormal. So you basically have alpha sub I squares, EI, HEI. If I replace note that I goes from 1 and not 0, because the energy of the smallest alpha 0 is zero energy state. Right, it's a zero energy state, so I just skipped it. Now, if I replace EIs by E1, the energy can only go down because the first excited state. So this is bigger than this, but I can bring this outside and sum over alpha i's. This gives me a half. So the gap is smaller than or equal to 2 times phi h phi. Now the question is, what phi should you use? This is for any phi the case, but like you want a clever phi. The phi we used is, if this is the ground state, uniform superposition of Motzkin walks, you multiply it by e to the area. So this inspired Klitsch and others to come with their model. So e to the 2 pi I, some phase, theta is some number, times the area under the Motzkin walk, times the Motzkin walk. And if you do that, again, this is phi. This is the overlap condition. It just will be a sum of these phasors. And the way integrals work is that if you take the n to infinity, this converges to an integral. So will be from 0 to infinity. This is the probability density. So this is the probability density of areas under the Motzkin walk. That's just how integrals work, right? You have a summation. A of p becomes x. The summation gives you a dx, but you have to multiply by the measure. So this is the probability density of area under Motzkin walks. But this probability density, by universality of Brownian motion, is just a probability density of Brownian excursions. So the Brownian motion has various universality classes. One is, there's Brownian bridge, where you start here and end anywhere, can go above or below. Excursions are exactly those that start at 0, end at 0, don't go negative. So you get this excursion. And they have some probability density, which is actually the area under the area function, it turns out. So this is textbook material. And you can actually write it down. All right, it's in terms of, uh, hypergeometric functions, whatever, looks scary. So I just plotted this for you here in Mathematica, and this is, by the way, you guys recognize this formula? So if this is the function, what is this? Fourier transform, right? So for theta, for theta equals 0, this integrates to 1, like it should, because of probability density, right? Because this goes away. If theta is very large, it should kill the integral. So here I'm plotting for you that characteristic function. The Fourier transform starts at 1 and goes down to 0. And the theta that I've been talking about, you use the standard of deviation here to get maximum cancellation. You put it in, and you get 1 over n squared as the upper bound. The rest of it is just like shoving it through. I just wanted to tell you what the phi was. The rest of it is just like machismo math. You just grind it. And that was the upper bound. Now I want to tell you about the lower bound. And this is pretty cool, actually. It's been pretty useful. So if you have a frustration-free local Hamiltonian, that's also stochastic. And stochastic means it doesn't have the sign problem. So it's real, and off-diagonals are non-positive in some convenient basis. Then you can always relate your Hamiltonian to a classical Markov chain. And the way you do it is you look at this is the identity matrix, so del xy, minus some to be determined beta, square root of, this is the component in the stationary distribution of the Markov chain, pi x over pi y, and the matrix element of H. Now because of this minus sign, the gap of the Hamiltonian, which is the smallest two eigenvalues, will be related to the gap of the Markov chain, which is defined to be the distance between the two largest eigenvalues. The gap of a Markov chain is 1 minus lambda 2. It's always 1, the largest eigenvalue. And then, so that relates the gap of the Hamiltonian to the gap of actually classical Markov chain. So now you can unleash everything you know about Markov chains to prove the gap here, and that will immediately give you a gap here. Okay? Now this is not always easy to do because proving gaps of Markov chains is also like active area of research. Sometimes you can do it, sometimes you cannot. But this helps. And this is something we use and I've used in other contexts as well. So I'm just going to tell you the proof idea. So I had a Hamiltonian, right? And it had these two terms, two types of terms. One was exchanging steps with vacuum. The other one was this interaction term, up, down, going to flat, flat, and back. Any questions so far? Or so I'm going to tell you that the gap is lower bounded by a polynomial. Okay? Yeah. Yeah. That's right. That's right. Because of minus sign inequalities, right? Yeah, that's right. And the gap of the Markov chain is defined to be the difference between the two largest eigenvalues. When we multiply that by minus, big positive ones become big negative ones. Right? So it becomes the actual gap. Okay, so far I haven't done anything. You can just rearrange the terms into like h moves and h int interaction. But then if you multiply h interaction by small epsilon, which is less than or equal to 1 and greater than 0, and these are projectors, it's easy to see that the gap can only go down. Because it's a positive operator, and you multiply some of the projectors by something smaller than 1, so the energy can only decrease. The ground state is going to be the same. All right? So this gap is lower bounded by gap of h epsilon, but there is a nice lemma. It's basically first order degenerate time independent perturbation theory, but done right we call it projector lemma by Kepikatayev and Regev. It says the following. It says if you can prove that the gap of h move is lower bounded by 1 over a Paulian n, and you can prove that the gap of h effective is lower bounded by 1 over Paulian n, where h effective is defined to be the restriction of h int onto the ground subspace of h move. So h move has some ground subspace. You just project your interaction term onto it. You have a new Hamiltonian, call it h effective. if you can prove this, which is not necessarily easy, then this implies that the gap of h epsilon that you started with is greater than 1 over n to a constant. But then you're done, because that lower bounds the actual gap. That's the logic of how we're going to prove this. So the good thing is that h move is just like Heisenberg's spin half chain, right? Like it doesn't see up or down. It's like 0, 1, 1, 0. And the gap is, from to a physicist, this is trivial, but there's a QED attached to this. This is just spin wave theory. You get 1 over m squared. It's 1 minus cosines. So, but you can also formalize it. It's 1 over m squared as n goes to infinity. So what remains to be done is to prove the gap of h effective, because this is this piece, and h effective is what we need to do. And this was a hard piece to do. How much do I have? Maybe like 3 minutes, 4 minutes? Okay. Yeah. So let me tell you what h effective is. So pi move takes as, so if this is a Motzkin walk, this is the corresponding Dick walk, where I just took away the zeros, flats. So that's all. If you take this away, you bring them together, you get this piece. And if you take this away, you bring them together, this piece. So pi is an isometry. It takes as input a Dick walk, and of size, say, 18. And it takes that one term and makes a uniform superposition of all Motzkin walks by putting flats for n minus 18 places that with the corresponding Dick walk. Like if you take away the zeros, you get this Dick walk. But it's a uniform superposition, otherwise, on all Motzkin walks with such a Dick walk restriction. Then, okay, guys, can I just use the board quickly? Maybe it helps. So you have a pi. This takes as input a Dick walk of size, say, 2k. Okay? This, in result, gives you a uniform superposition of all Motzkin walks on 2n, whose restriction will give you this particular Dick walk. Okay? And then H interaction looks at this, and all it can do is if it sees a couple of flats, it can replace it with a peak. Or if there's a peak, it can chop it out and give you two flats. So effectively, you have a Motzkin walk, again another Motzkin walk, plus minus one peak. So maybe you lost two zeros and you got a peak, or you lost a peak and you got two zeros. And this does the opposite. It grabs the Motzkin walk and spits out a Dick walk of length 2k plus minus 2, depending on whether you lost the peak or you gained the peak. Okay? So the effect of, this is H effective. The effect of H effective is a random walk. So if you think of all the Dick walks as like nodes on a hypergraph, they're edges between two Dick walks if and only if they differ by a single peak. So you have formally a Markov process on this space of Dick walks. And then you can use, there are various ways to prove the gap. It's usually the gap to search. I mean, it's not, we use the canonical path method, which basically says, if you can prove you can go from any Dick walk to any other Dick walk through a path that is not used by many other associations, then the trap, so the way you prove the gap is using the following idea. The gap and mixing time are intimately connected. So if a Markov chain has a big gap, it mixes rapidly. That means you can go from any state to any other state in polynomial time. All right? So one way to get the gap is to prove rapid mixing of the Markov chain. That's what the canonical path method gives you. And what you need to show is that you can indeed go from any arbitrary node to any other arbitrary node. There exists a set of paths you can take on which you will not get stuck exponentially long. So you can go relatively fast from one to the other. And you can prove this if you can prove like the set of edges you take from one to the other, none of them is really congested. So if you think about two houses in Maryland, you can't go from one to the other. If all the streets, alleys, and highways you take, none of them you get stuck in exponentially long. And if the total path is like polynomial length, you polynomial time you get from one to the other. Does that make sense? Kind of? No? Okay, so you go from one to the other fast. If nowhere, you get stuck long. And that you can prove if you can prove that there exists such canonical set of paths. And to do that, we had to prove a new result in statistics of dick walks that says you can organize dick walks of larger and larger size in such a way that no parent has more than 4 children. And that's actually optimal because the number of walks, the Catalans, scale as 4 to the k. And then, you can show that you can go from any walk to any other walk by starting from this walk and nothing, shrink this by 1, grow that by 1. And you keep doing this till you hit your target. So let me just give you one example of a canonical walk. Suppose this is my house, and this is your house. And so I can go from this, concatenate with nothing, get this. Now here, I cut out this one peak, and I got this, and I inserted that one peak here. Right, I concatenate, I get that. And then here, maybe I chopped out this one peak, or I could have chopped out this peak to get this, and I inserted next to the other one, concatenate. Lastly, well, not lastly. Then I chop out this one peak, I get this. Then I insert it in the middle here, but with the right color red, I get this, concatenate. And then at the very end, I chop this one out and put it in the middle here with the red color, and I'm at your house. So it's an example of a canonical path. We prove their existence, but we don't have an algorithm for finding the canonical path. So it's a non-constructive proof. But it does the job. Gives you 1 over n to a, I believe 11 halves is what I recall as the gap. Okay, so maybe the last part was a little technical, but this is the idea. And so maybe let me just leave it at that. And thank you for your attention. Thanks. Yeah. Yeah. Right. So if you want to know how the gap scales, you need a lower bound. If you want to show gaplessness, all you need is an upper bound. If you want to, for example, show that its gap is exponentially small, all you need is an upper bound that's exponentially small. But to get a polynomial gap, you have to show that upper and lower by polynomial, exactly to rule out exponentially small. And lower bound you need because that's not enough, because what if the gap is a constant? Right. Yeah. Yeah. Mm-hmm. 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 Uh-huh. Uh-huh. So, these are projectors. So you can following you can do. You can multiply all the projectors by positive numbers, whatever they may be. It will not change the ground state. So there is this manifold of stability. So because this frustration freeness gives you such a stability. See what I mean? So if you have yeah, I don't know. I don't know. I don't know how you would prove that. But the stability statement I can give you is the following: that you can actually multiply the local terms by random constants even, and this area law violations, none of these will change. But the local partition, we can talk. I mean,